Today we are going to discuss properties of Z transform. The first property is linearity and the statements is if x1 of n, if we take Z transform of x1 of n, we get x1 of z with ROC is equal to R1, and if we take Z transform of x2 of n, we get x2 of z with ROC is equal to R2. Then a into x1 of n plus b into x2 of n, if we take Z transform, we get a into x1 of z plus b into x2 of z with ROC containing R1 intersection with R2. Z transform of a linear combination of signals is the same linear combination of their Z transforms. Linearity property helps us to find the Z transform of a signal by expressing the signal as a sum of elementary signals for which the Z transform is already known. For example, determine the Z transform of the signal x of n is equal to b to the power mod n, where b is greater than 0. X of n is equal to b to the power n into u of n plus b to the power minus n into u of minus n minus 1. Then x of z is equal to summation n is equal to minus infinity to infinity b to the power n into z to the power minus n into u of n plus summation n is equal to minus infinity to infinity b to the power minus n into z to the power minus n into u of minus n minus 1. Then the summation starts from 0 because it is given u of n. So summation n is equal to 0 to infinity b to the power n into z to the power minus n plus once again summation starts from minus 1 infinity and ends with minus 1 because it is given u of minus n minus 1. Summation n is equal to minus infinity to minus 1 b to the power minus n into z to the power minus n. Then by putting n is equal to minus m, we get when n is equal to minus m, when n is equal to minus infinity, m is equal to infinity, and when n is equal to minus 1, we get m is equal to 1. So applying these limits into the summation, we get summation n is equal to 0 to infinity b to the power n into z to the power minus n plus summation m is equal to infinity to 1 b to the power m into z to the power m, which is equal to summation n is equal to 0 to infinity b into z inverse to the power n plus summation m is equal to 1 to infinity b into z to the power m. Then by putting L is equal to m minus 1, then we get m is equal to 1, L is equal to 0, and when m is equal to infinity, L is equal to infinity. Then the summation n is equal to 0 to infinity b into z inverse to the power n plus summation L is equal to 0 to infinity b into z to the power L plus 1. Then x of z is equal to 1 divided by 1 minus b into z inverse plus bz divided by 1 minus bz. Then x of z is equal to 1 divided by 1 minus b into z inverse plus 1 divided by bz minus bz by bz. Then x of z is equal to 1 divided by 1 minus b into z inverse minus 1 divided by 1 minus b inverse into z inverse. For convergence, bz inverse is less than 1 and bz is equal to 1. That is, b by z is less than 1 and mod of z is less than 1 by b. Then ROC is mod of z is greater than b and mod of z is less than 1 by b. The first case, if b is greater than 1, then No convergence occurs. It has shown in the given figure 1 by b and b also drawn. And in the second case, if b varies between 0 and 1, in the figure it has shown it varies between 0 and 1, then the ROC is mod of z is between b and 1 by b. Next property is time shifting property. If we take the transform of x of n, we get x of z with ROC is equal to R. Then z transform of x of n minus k, we get z to the power minus k into x of z with ROC is equal to R, except for the possible addition or deletion of the origin or infinity. Because of the multiplication by z to the power minus k, for k is greater than 0, poles will be introduced at z is equal to 0, which may cancel corresponding zeros of x of z at z is equal to 0. Consequently, z is equal to 0 may be a pole of z to the power minus k x of z, while it may not be a pole of x of z. In this case, ROC of z to the power minus k into x of z equals the ROC of x of z, but with the origin deleted. Similarly, if k is less than 0, zeros will be introduced at z is equal to 0, which may cancel corresponding poles of x of z at z is equal to 0. Consequently, z is equal to 0 may be a 0 of z to the power minus k into x of z, while it may not be a pole of x of z. In this case, z is equal to infinity is a pole of z to the power minus k into x of z, and thus the ROC for z to the power minus k into x of z equals the z transform of x of z, but with z is equal to infinity deleted. For example, by applying the time shifting property, determine the z transform of the signals x2 of n and x3 of n for the z transform of x1 of n. It is given x1 of n is equal to 1, 2, 5, 7, 0 and 1. x2 of n is equal to 1, 2, 5, 7, 0, 1. x3 of n is equal to 0, 0, 1, 2, 5, 7, 0, 1. Then x1 of z, if we take z transform of x1 of n, we get x1 of z is equal to 1 plus 2z inverse plus 5z to the power minus 2 plus 7 into z to the power minus 3 plus 1 into z to the power minus 5. If we take z transform of x1 of n, we get x1 of z, then x2 of n is equal to shifted by 2 units x1 of n plus 2. If we take z transform, we get z square into x1 of z. Then x2 of z is equal to z square into x1 of z is 1 plus 2z inverse plus 5z to the power minus 2 plus 7 into z to the power minus 3 plus 1 into z to the power minus 5, which is equal to z square plus 2z plus 5 plus 7z inverse plus 1 into z to the power minus 3. Then x3 of n is equal to x1 of n minus 2. If we take z transform of that, we get z to the power minus 2 into x1 of z. Then x2 of z is equal to z to the power minus 2 into x1 of z, that is 1 plus 2z inverse plus 5z to the power minus 2 plus 7z to the power minus 3 plus z to the power minus 5, which is equal to z to the power minus 2 plus 2 into z to the power minus 3 plus 5 into z to the power minus 4 plus 7 into z to the power minus 5 plus 1 into z to the power minus 7. Then ROC does not include z is equal to infinity. Next property we have time expansion. Discrete time concept of time expansion is that of inserting a number of zeros between successive values of a discrete time sequence x of n. Xk of n is equal to x of n by k if n is a multiple of k and 0 if n is not a multiple of k. K minus 1 zeros inserted between successive values of the original signal. If take the transform of x of n, we get x of z with ROC is equal to R. Then if we take the transform of xk of n, we get x of z to the power k with ROC R to the power 1 by k. Next property is time reversal property. If we take z transform of x of n, we get x of z with ROC is equal to R. Then z transform of x of minus n, we get x of 1 by z with ROC is equal to 1 by R. Time reversal or reflection corresponds to replacing z by z inverse. Hence, if ROC is of the form A is less than mod z less than B, the ROC of the reflected signal is A is less than 1 by mod z is less than B, or 1 by B is less than mod z less than 1 by A. Next property is multiplication by exponential sequence, that is scaling in the z domain. The statement is if we take z transform of x of n, we get x of z with ROC is equal to R. Then if we take z transform of alpha to the power n into x of n, we get x of z by alpha with ROC alpha into R. The notation alpha into R implies that the ROC boundaries are multiplied by mod alpha. If R is A is less than mod Z less than B, then new ROC is mod alpha into A is less than mod Z is less than mod alpha into B. Next, we are going to discuss about conjugation property. The statement is if Z transform of x of n is x of z with ROC is equal to R, then Z transform of x star of n is x star of z conjugation with ROC is equal to R. Thus, if x of z has a pole or 0 at z is equal to z0, it must have a pole or 0 at complex conjugate point z is equal to z0 star. Next property is convolution property. The statement is if the transform of x1 of n is x1 of z with ROC is equal to R1 and z transform of x2 of n is x2 of z with ROC is equal to R2, then the transform of x1 of n star x2 of n is x1 of z into x2 of z with ROC containing R1 intersection R2. So proof for this property is let x of n is equal to x1 of n star x2 of n. Then x of n is equal to summation k is equal to minus infinity to infinity x1 of k into x2 of n minus k. Then the transform of x of n is x of z, which is equal to summation n is equal to minus infinity to infinity x of n into z to the power minus n, which is equal to summation n is equal to minus infinity to infinity summation k is equal to minus infinity to infinity x1 of k into x2 of n minus k into z to the power minus n. Then x of z is equal to summation n is equal to minus infinity to infinity x1 of k into summation k is equal to minus infinity to infinity x2 of n minus k into z to the power minus n, which is equal to x2 of z summation n is equal to minus infinity to infinity x1 of k into z to the power minus k, which is equal to x2 of z into x1 of z. For example, compute the convolution of the two signals x1 of n and x2 of n given below. x1 of n is equal to 1, minus 2, 1 and x2 of n is equal to 1, where n varies between 0 to 5 and 0 elsewhere. Then if I take z transform of x1 of n, I can write x1 of z as 1 minus 2z inverse plus z to the power minus 2. And if I take z transform of x2 of n, I get x2 of z as 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3 plus z to the power minus 4 plus z to the power minus 5. Then convolution property x of z is equal to x1 of z into x2 of z. Multiplying x1 of z with x2 of z, we get 1 minus 2z inverse plus z to the power minus 2 into 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3 plus z to the power minus 4 plus z to the power minus 5, which is equal to 1 minus z inverse minus z to the power minus 6 plus z to the power minus 7. So I can write x of n as, by taking inverse z transform, x of n is equal to 1 minus 1, 0, 0, 0, 0, minus 1 and 1. Next, we are going to discuss about differentiation in the z domain. The statement is z transform of x of n is x of z with ROC is equal to R, and z transform of n into x of n, we get minus z into differentiation of x of z divided by z dz with ROC is equal to R. The proof for this: consider x of z is equal to summation n is equal to minus infinity to infinity x of n into z to the power minus n. Then differentiation of x of z, that is d of x of z divided by dz, is equal to summation n is equal to minus infinity to infinity x of n into minus n into z to the power minus n minus 1, which is equal to minus z inverse into summation n is equal to minus infinity to infinity n into x of n into z to the power minus n, which is equal to minus z inverse into z of n into x of n. Both transforms have same ROC. For example, determine the z transform of the signal x of n is equal to n into a to the power n into u of n. So if we take z transform of x1 of n, which is equal to a to the power n into u of n, we get x1 of z is equal to 1 divided by 1 minus a into z inverse with ROC mod z is greater than mod a, and n into a to the power n into u of n. If we take z transform, we get x of z is equal to minus z into differentiation of x1 of z divided by dz, which is equal to a into z inverse divided by 1 minus a into z inverse square. with ROC mod Z is greater than mod A. Next property is correlation of two sequences. If Z transform of x1 of n is x1 of Z with ROC is equal to R1, then Z transform of x2 of n is x2 of Z with ROC is equal to R2. Then R of x1 x2 of L, that is correlation, is equal to summation n is equal to minus infinity to infinity x1 of n into x2 of n minus L. If we take Z transform, we get x1 of Z into x1 of Z inverse, which is equal to correlation of x1 into x2 of Z, that is R represents the correlation. The ROC of R x1 x2 of Z is at least the intersection of that of x1 of Z and x2 of Z inverse. For example, determine the autocorrelation of the signal x of n is equal to a to the power n into u of n. Then correlation of Z is equal to x of Z into x of Z inverse, which is equal to 1 divided by 1 minus A into Z inverse into 1 divided by 1 minus AZ. Then ROC is mod Z is greater than mod A and mod Z is less than 1 by mod A, which is equal to 1 divided by 1 minus A into Z plus Z inverse plus A square. Then ROC is mod A is less than mod Z, which is less than 1 divided by mod A. Next, we are going to discuss about initial value theorem. If x of n is equal to 0, n is less than 0, then x of 0 is equal to limit z tends to infinity x of z, where x of z is equal to summation n is equal to 0 to infinity x of n into z to the power minus n, which is equal to x of 0 plus x of 1 into z inverse plus x of 2 into z to the power minus 2 plus so on plus x of n into z to the power minus n and so on. As z tends to infinity, z to the power minus n tends to 0 for n is greater than 0, whereas for n is equal to 0, z to the power minus n is equal to 1, so that limit z tends to infinity x of z is equal to x of 0. As one consequence of initial value theorem for causal sequence, if x of 0 is infinite, then limit z tends to infinity x of z is finite. With x of z expressed as the ratio of polynomials in Z, the order of the numerator polynomial cannot be greater than the order of the denominator polynomial, or equivalent the number of finite zeros of x of z cannot be greater than the number of finite poles. For example, find the initial value x of 0 for the signal with the transform. X of z is equal to z cube minus 3 by 4 z square plus 2z minus 5 by 4 divided by z minus 1 into z minus 1 by 3 into z square minus 1 by 2z plus 1. Then x of 0 is equal to limit z tends to infinity x of z, which is equal to limit z tends to infinity. If I take z cube outside, becomes z cube into 1 minus 3 by 4z plus 2 divided by z square minus 5 divided by 4 into z cube divided by, if I take z outside, z into 1 minus 1 by z into z into 1 minus 1 divided by 3z into z square into 1 minus 1 divided by 2z plus 1 divided by z square, which is equal to 0. Next is final value theorem. From the time shift theorem, we have z of x of n minus x of n minus 1 is equal to 1 minus z inverse into x of z. And summation n is equal to 0 to infinity x of n minus x of n minus 1 into z to the power minus n is equal to limit n tends to infinity summation n is equal to 0 to n x of n minus x of n minus 1 into z to the power minus n. Let z is equal to 1. Then limit z tends to 1. 1 minus z inverse into x of z is equal to limit n tends to infinity summation n is equal to 0 to n x of n minus x of n minus 1, which is equal to limit n tends to infinity x of n is equal to x of infinity, assuming x of infinity exists. We have one limitation. Final value theorem can be applied only if the final value exists. For example, final value theorem cannot be applied to find x of infinity of the signal x of n is equal to 2 to the power n into u of n. One example on final value theorem. Find the final value x of infinity for the signal with the transform x of z is equal to z cube minus 3 by 4 z square plus 2z minus 5 by 4 divided by z minus 1 into z minus 1 by 3 into z square minus 1 by 2 into z plus 1. Then x of infinity is equal to limit z tends to 1 1 minus z inverse into z cube minus 3 by 4 z square plus 2z minus 5 by 4 divided by z minus 1 into z minus 1 by 3 into z square minus 1 by 2z plus 1, which is equal to limit z tends to 1 z minus 1 divided by z into z cube minus 3 by 4 z square plus 2z minus 5 by 4 divided by z minus 1 into z minus 1 by 3 into z square minus 1 by 2 into z plus 1, which is equal to 1 minus 3 by 4 plus 2 minus 5 by 4 divided by 1 minus 1 by 3 into 1 minus half plus 1. This is by putting z is equal to 1. So after simplification of the given equation, we get the final answer as 1.